So one of the really good applications for our first order linear difference equation, our y prime plus py equals q solving technique, has to do with tank questions, brine questions. So let's just read through the question. We've got a 20-liter tank is initially full of fresh water. A brine solution, so a saltwater solution, is being pumped in with a concentration of 0.01 kilograms per liter, and that flows in at a rate of 2 liters per minute. Now, if I stop and I say, here I made a picture in paint to show you, if I say, oh look, it's 0.01 kilograms per liter at 2 liters per minute, and I were to ask you how many kilograms per minute are coming in, you'd go 0.02, and then I'd say, how did you get that 0.02? And you'd say, well, it's 0.01 kilograms per liter times 2 liters per minute. If I multiply those two things, it should be 0.02 kilograms per minute. The liters on the bottom of the kilograms per liter cancel with the liters on the top of the liters per minute. And anyway, the inflow of salt is 0.02 kilograms per minute is what you would say. That's the inflow in kilograms per minute. And then I'll say, well, what did you really do? You multiplied a concentration, kilograms per liter, times the flow rate, liters per minute. You multiplied concentration times flow. All right, let's go back to the question. The tank is well mixed and the salt water, the brine, flows out at the same rate of 2 liters per minute. All right, now let's stop here. Another thing. We got 2 liters, I'll take my picture here. It took me like 20 minutes to make this. You got 2 liters per minute flowing in and 2 liters per minute flowing out. If 2 liters per minute flowing in and 2 liters per minute flowing out, the volume, the amount of water in the tank is constant. We're going to end up having two different kinds of these word problems. Ones where the volume is constant, like this one, and ones where the volume is not constant, like the next one we're going to do. So in questions where the volume is not constant, it'll be different, like 2 liters per minute flowing in and then, not 2 liters per minute, either more or less flowing out. But in this case, it's 2 liters per minute flowing in, 2 liters per minute flowing out. The volume is constant. So it's a 20-liter tank full of fresh water. So there's always going to be 20 liters of liquid in the tank. 2 liters per minute flowing in, 2 liters per minute flowing out. All right, so I'm going to create the differential equation that models the salt in the tank. Solve it. We're going to call y of t the kilograms of salt in the tank at time t. And our differential equation then, y prime, well, y prime, we mean dy dt, and the y is measured in kilograms, and the time is measured in minutes, so this y prime is in kilograms per minute, and you already said that it's 0.02 kilograms per minute flowing in. And I asked you how you got it, and you said you multiplied, or I said, it was just me saying it, but you guys are listening, that you multiplied the flow rate times the concentration. So I'm going to do the same thing for the out. I'm going to do the flow rate, which is 2 liters per minute, and I need to multiply that by the concentration in the outflow. Now here's where the term well mixed comes in. Well mixed, by well mixed we mean that the tank is homogeneous. The concentration over the top part of the tank is the same as the concentration over in this corner of the tank, is the same as the concentration in the middle, is the same as the concentration here, is the same as the concentration in the outflow. By well mixed, that means the concentration is the same throughout the whole tank, so the outflow of the concentration is the same as the concentration in that tank. What is the concentration in that tank? Well, concentration is measured in kilograms per liter, and I know the bottom part, I know the liter, it's 20 liters. That's how much liquid's in the tank. How many kilograms of salt are in the tank? Well, that changes. The question said it started out as fresh water, so initially there's no salt in the tank. Initially, the y is equal to 0. Y naught is equal to 0. Y naught is, that's going to be our initial condition that we're going to get the constant from. So we'll make note of that for later. But initially full of fresh water means when T is equal to 0, Y is equal to 0. Anyway, let's get back to we need to know the concentration. I have the flow rate. This flow rate is 2. This is in liters per minute. I need to multiply this by some sort of a kilograms per liter, and I already know the liters is a constant 20. What's the kilograms? Well, we were saying that changes. It starts at 0, but as I start to pump in salt water, it should get saltier and saltier and saltier. So it does change. Oh yeah, that's our Y of T. How many kilograms of salt are in the tank? Y. So that goes on top. If I were to multiply these two things together, let's clean that up. I'm going to get a Y prime is equal to 0.02. The units of that 0.02 are kilograms per liter, and this 2 is going to cancel with this 20, so minus a tenth. And this liters cancels with this liters, so our units are kilograms per minute. Kilograms per minute minus kilograms per minute is kilograms per minute. Y, that Y is still there. There's our differential equation. Create the differential equation, done. All we have to do now is solve it. Oh, and I have my initial condition. It says it's fresh water, so initially Y naught is equal to 0. There's our differential equation that we can solve, and we know what kind it is. It's a Y prime plus Py equals Q. First order linear. It's also separable, but we're going to solve it as first order linear, as a Y prime plus Py equals Q. Now, before we solve it, get the integrating factor, etc., just go back to the words for a second. If I were to take this initially fresh water and continue to flush it out with this 0.01 kilogram per liter salt solution, and I've let it go forever, eventually, how much salt will be in the tank? Well, eventually, if I flush it out with 0.01 kilograms per liter forever, eventually it's just going to be 0.01 kilograms per liter in the tank as well. 20 liters, 0.01 kilograms per liter. I would expect there to be, what, 0.2 kilograms of salt in that tank? 0.01 times 20. That's how much salt I would have expect there to be eventually in the tank. All right, let's go back and solve. I need an integrating factor. So the integrating factor is going to be e to the integrate P T over 10. That's my integrating factor, and I'm going to multiply it through all three sides of this equation. So let's do this first. Now I'm going to integrate both sides. I know that this side, I know the left-hand side just is going to integrate to be y times the integrating factor. The right-hand side is going to integrate to be 0.2 now plus a constant. So now from this step to this step is me integrating both sides. Let's get the constant. We have one constant of integration. That's where I'm going to use my initial condition. If I make t is equal to 0, then y is equal to 0. That tells me that c has to be minus 0.2. And so there's our implicit solution. Let's get the explicit solution. To get the explicit solution, all I'm doing is taking the implicit solution and multiplying everything by e to the minus t over 10. There's my explicit solution. That's how much salt is in the tank at time t. And I do see, just like I expected, if I let t go to infinity, this piece goes to 0 and I end up with 0.2 kilograms, like we figured from the words. So there's our first tank question. The next one we're going to do, the volume will change. The inflow rate won't equal the outflow rate. But before we leave this question, let's just think about where the new parts of this ended. The new parts of this ended here, right? As soon as I was at this step, now it's a first order linear, it's just plain solve. The new parts that we learned was just the y prime is the in minus out, and both the in and the out were multiplying a flow rate times a concentration. Let's take a look at another example. So now I've got a 100-liter tank. It's initially half full of fresh water. So initially there's 50 liters of water, of fresh water in the tank. A pipe pumps in salt water at a concentration of 2 kilograms per liter at a rate of 4 liters per minute. If I stop now and say, all right, we got 2 kilograms per liter and 4 liters per minute, how many, because I remember our y is the amount of salt, so our y prime would be equal to in minus out, and this y prime would have the units of kilograms per minute, because it's y prime, it's dy divided by dt. How many kilograms per minute are going in? 2 kilograms per liter and 4 liters per minute gives me 8 kilograms per minute going in. I would just multiply those two values and watch the liters cancel, minus the out. Well, okay, the tank is well mixed. We remember that tells us that the concentration in the tank is the same as the concentration in the outflow. The outflow drains at 2 liters per minute. Oh, wait a minute. We got, or wait a moment, let's say. We got 4 liters per minute going in and 2 liters per minute going out. So if I go back to my paint diagram, this is, if I go back to my paint diagram and painfully erase this, we got 4 liters per minute going in, and I got 2 liters per minute going out. So that means the volume must be going up, because every minute I got 4 liters going in and only 2 liters coming out. So the volume of the tank must go up 2 liters every minute. We could even make a formula for that. Let's do that. The volume as a function of time is equal to the initial volume plus the inflow minus the outflow times time, which I guess is, well, what we would do here would be 50 liters plus 2t. Now, does this make sense with our, words? You get 4 liters per minute flowing out. Initially, when t is equal to 0, this 100-liter tank is supposed to be half full. Yeah, if I make t equal to 0, I get 50 liters. If I let this system run for 10 minutes, then 4 liters per minute going in and 2 liters per minute going out. Every extra minute there's 2 liters, 10 minutes, extra 20 liters should be 70. Yeah, this checks out. If I make t equal to 10, the volume is 70. So let's go back to the out. There's the in kilograms per minute. Now the out is supposed to be in kilograms per liter, and I know what the liters, I know what the volume is. It changes. There's the volume in liters. How many kilograms? Y, because that also changes because it's initially full of fresh water and we're pumping in salty water, so that's y of t. There's kilograms per liter. I need to multiply that by 2 liters per minute, and I get the kilograms per liter and the liters per minute. The liters cancel out, and I end up with kilograms per minute. And again, initially, because they said it was fresh water, I guess it doesn't always have to be fresh water, but in this case, y naught is equal to 0. Let's clean that up. I get a y prime plus, okay, I'm going to move this piece over to the other side, but I'm going to cancel this 2 off before I move it over. So I'm going to make this 25 plus t times y equals 8, and I'll still have my initial condition here. Now, let's stop. The words are over. Here's my differential equation. It's a y prime plus py equals q. It's a first order linear. And there's my initial condition. Now we just have to go about solving it. We need an integrating factor. And our integrating factor has an e to the ln. And we remember from our first order linear that we need to use the property of inverse functions and cancel those out. So our integrating factor is 25 plus t. I'm going to take the original y prime plus py equals q question and multiply all three sides by 25 plus t. Now, this 25 plus t and this 25 plus t can cancel. I'm not going to bother though, because I'm going to integrate both sides, and I know that this left hand side integrates to be y times the integrating factor. I need to integrate this side. That's going to be, that's a constant, 25t plus, what's that going to be, t squared over 2 plus a constant. Now so that's me integrating both sides of the equation. We'll get the constant by noting that y naught is equal to 0. When I make t equal to 0, y is equal to 0. So that's going to be 0 here, 0 here. So then c is equal to 0 in this case. So if I solve for the explicit solution, let's multiply this 8 through the bracket. There's the amount of salt in the tank at time t. And to be perfectly good, we should note to self here that this formula really only works for t's between 0 and 25 because it's a 100-liter tank, and at 25 minutes the tank is full. Remember, it started at 50 and it goes up 2 liters per minute. So I don't know what happens after that. Does it, is there a lid? Does the liquid back up? Does it spill over? We don't know. So our formula is really only good for the first 25 minutes. This one is an example of what happens if the volume is changing, if the flow rate in is different from the flow rate out. So I think I can make a sort of a general form for this. Y prime is equal to inflow times in concentration minus y over the volume, and we have a formula for the volume. Remember, these are in flows and out flows, and I need to multiply that by the outflow number. If the inflow and the outflow are the same, this 50, this is our initial volume. Let's make that a V naught. Let's make that a V naught for initial volume. So that's sort of a structure that we followed in both these two examples. In the first example, the inflow and the outflow were the same, so the V was just the V naught. In the second example, they were different, so we got a function of time on the bottom here in the denominator.